All right, take a look at section 2.1 here. We look at analyzing the graphs of functions. We get into talking about increasing, decreasing, and constant intervals within a function graph. All right, so we see here we've got the definitions of what it means to be a increasing, decreasing, and constant function. Increasing function is a function that rises from left to right. It increases in value. Right, as x gets larger, y will get larger. An example, so we want to write down here an example of what a increasing function would be. We can go back to our previous unit and talk about linear functions, right, graphs of lines. We know example of an increasing function would be a linear function of form y equal mx plus b, where m is greater than 0. Right, rising from left to right, increasing function. So again, positive slope. Right, no matter where you're on that graph, as you move from left to right, you're always going up. Right, you're increasing. So as x is getting larger, y is getting larger. If you were looking at on the x and y axis. An example of decreasing function. We know function is decreasing if it's going down or dropping as we move from left to right. And one thing you want to make note is you want to always analyze your graphs from left to right along the domain of the graph. So you're going to look along the x-axis you observe in your graph and see what your graph's doing. Is it going up, is it going down, or is it going straight across? Determine these intervals. So decreasing function, just going back to our previous unit, looking back at a linear function, here's slope-intercept form. Where m is less than 0, we know it's decreasing. It's going down. There's an example of a decreasing function. Looking at a constant function, a function that stays the same, it doesn't increase or decrease. We know we're looking at an example of a horizontal line. If we want to go back to graphs of lines, so y equal to b, right, where slope is 0. Which means a horizontal line, right, stays the same. Doesn't increase or decrease in value. Y is constant. So taking that, let's put all this together. In our next example, we've got a piecewise function graph. In a piecewise function, we've got different pieces of functions coming together to create a new function of x, which we have here. In this example, we have some different pieces of linear functions. Different pieces of lines that are coming together. And you can clearly see this is a function graph, right? Every x value on this graph has exactly one y value. Most it crosses at one point. And if you notice, even at -3, right, you got an open circle and a closed circle. So it is crossing at one point only. So yeah, if you were looking at your vertical line test, just to review definitions of functions, we can see clearly we've got a function of x. What I want to do is not only determine the intervals on where this function is increasing, decreasing, and constant. Let's also state the domain and range. So let's review a little bit while we're at it with what we've already talked about, right, in our previous unit. So as I observe this graph, all right, let's start with this first interval that I see. As I observe a graph, I'm going to observe a graph along the domain. So my graph begins over here at -5 on the x-axis. Right? We could even plot this ordered pair. That's the ordered pair -5, 1. Well, I see a decreasing interval come into play. All right, so let's write that over here. Where is this graph decreasing? So give me the intervals of decrease. So as we observe the graph, we're going to look left to right along the x-axis. So if you look between -5, right, and -3, our graph is decreasing, right? As x is getting larger, y is getting smaller. So that would be a decreasing interval. So over here, let's write that in here. Now we write in our decreasing, increasing, constant intervals. We are never going to use brackets. So we're looking between the values of x equal -5 and x equal -3. So all values greater than -5 and less than -3. So again, these are x values. So keep that in mind. That's where it's decreasing in value. So we're looking at where it's decreasing along the x-axis. So again, if you're looking at it as x, this is x greater than -5 and less than -3. Now as we move on, we see our graph change behavior. So as we get to -3 on the x-axis, we jump down here to the ordered pair of -3, let's say -5. Well, now our graph starts to rise from left to right, starts to increase in value. So let's go ahead and look at that. Let's see where we are on the x-axis as far as where we increase in value. So again, we've already observed where we're decreasing between -5 and -3. Well, now we're going up, we're increasing. So we'll put it in red here in a different color. So let's write in our increasing interval. And it's the only increasing interval in this graph. But between -3 and 0 on the x-axis, so I'll shade it in. Let's shade in these x values where it's rising from left to right. So all x values greater than -3 and less than 0. The graph is rising, increasing in value. As x getting larger, y is getting larger. So again, I'm shading in where I see that on the x-axis. And then as we look at our last interval, let's put it here in a different color, here in green. Let's look at this constant interval. So we have a constant interval come into play. So if you look between, let's say 0 and 2, right, and here, let's shade it in green. All x values greater than 0 and less than 2. My graph is staying the same. It's not going up. It's not going down. It's constant. All right, so there's our constant interval. So again, you're looking at this interval notation, right, that we're writing over here on the side, and that's the main thing you want to be observing. All right, now we've got one more piece to observe, and we're back to where we began, which is with a decreasing interval again. Right, it looks like between, let's write down this endpoint. This looks like the ordered pair 5, -5. So if you look between 2 and 5 on the x-axis, right, and I can shade it in, my graph is decreasing in value. So I have a second decreasing interval. I'm going to use my union symbol to state my second interval. And we have the values of x greater than 2 and less than 5. Right? So again, these are intervals of x values. So again, I just want to make that note. What we're saying here is all values of x greater than 2 and less than 5, right? It's decreasing. And we've shaded that in here on the x-axis. So you can see that interval, right here. Now that finishes off our intervals. Let's move to our domain and our range. So what's the domain and what's the range of this graph? Now remember, domain are all the real number values of x that satisfy this function. Well, as you look at this graph along the x-axis, we see our graph take place for all x values greater than or equal to -5, right? Our minimum domain value, right, is right here. So there's the min, right, domain value. It's our smallest x. And then you see everything in here. Even though the graph breaks here at -3, it goes down here and continues at -3. So -3 is on there, all right? And it goes all the way over until we get to 5, right? So there's our maximum, right? If you're looking at domain, right? Here's our max domain value. So as we look at domain, it's all x values greater than or equal to -5 and less than or equal to +5. So there it is in interval notation. There's a list of all the x values. And now let's look at the range. Now as I look at the range, and let's put it in a different color. All right, our range is where our graph takes place along the y-axis. It's a list of our y values. So with our graph in front of us, we can easily see that. So if you look at our graph, here's our minimum, here's our min range value. Right? It's our smallest y value. This is as far down the y-axis graph goes. Now, if I was shading in where I see my graph, right, I'm going from -5 to -2, and then I have a break in my graph between -2 and -1. There's a break in the graph. So with that said, we have a break in our range. So all y values greater than or equal to -5 and less than or equal to -2. Right? So there's those range values in here. We can write that over here just to see where it came from. And then it picks back up. We have a second interval of range values. Now you got to be careful here. At -1, we have an undefined value. So again, -1 is undefined. Right? That's a open circle. So again, that's not part of the graph. So we need a parentheses on -1. All y values greater than -1. And what? Less than or equal to +1. Right, is range. So we'll put in a 1 with a bracket. So there's a range. There's our range of y values. There are all the outputs for those x's, right, that we just looked at. So again, that's determining the range, right, looking at our graph along the y-axis. So domain is x values, range is y values. We won't forget that. So you can see your range values there. It's a good little review of a previous unit. All right, let's move on. We'll add to that. We'll continue the increase and decrease and constant interval topic. We're going to add to it some more characteristics of graphs of functions. We want to talk about relative extrema. Relative extrema are turning points in your graph. What we call relative maxima and relative minima points. A relative maxima point is an ordered pair at which our graph changes in behavior from increasing to decreasing. So a relative max point, behavior-wise, has this kind of shape going on. Right? That's the relative max point. At that point, right, that graph changes. From the left of that point, it's going up. To the right, it's going down. Right? There's an example of what that looks like. Now, in a relative minima, we have the opposite behavior. Decreases from the left and increases to the right. So you have that sort of U shape going on in your graph. You have a turning point where it turns from decrease to increase. So this is what we call a relative min point. Now, we're not saying this is an absolute minimum or maximum. Just relative to that part of the graph. We're going to have turns in our graphs. We're going to have these turning points come into play as we look at different functions of x, as we look at different polynomial functions. We'll see some good examples of that. And speaking of polynomial functions, let's take a look at a degree 3 cubic polynomial function. So as we look down here to our next example, it says use a given graph, determine any relative maximum or minimum for the given function, and the intervals for which the function is increasing or decreasing. And we could state domain and range while we're at it. Now in this function, I've graphed y equal x cubed minus 12x plus 2. Now you can put it in your calculator and reproduce this graph. But this is a graph that has a couple of turning points in it. So as we look at this graph, there's two ordered pairs that stand out. There's 2 points at which our graph changes behavior. So as we're looking at turning points, right here is a turning point. And let's label that. That looks like -2 for the x-coordinate. And it looks like 18 for the y-coordinate. And you could plug in -2 for x. -2 cubed minus 12 to -2 plus 2 is 18. And that point, that is the turning point. That is our relative maxima. Point. All right? So with that said, I want to make a mention of something. You'll see it written different ways. So down here at the bottom, I'm also going to, instead of writing the point, I'm going to write the relative maxima value. And the value is the output. The value is 18, and it occurs at a input of -2. So different ways to write that in. Now you also see in this graph another turning point, right? Down here at the ordered pair right here is a relative minima, right? At this point, it changes from decrease to increase. So up here at the max, it went from increase to decrease, increases from the left to -2, decrease to right -2. And down here at this turning point, it decreases from the left of x equal 2, which is where our turning point occurs, our relative minima, and increases to the right of it, 2. So again, change in behavior. So let's write in that ordered pair. As we're looking at that point, that's the ordered pair of 2, -14. That's our relative minima point. All right? So we want to, down here, I'm going to write it as a behavior relative min value. So sometimes it's asked for in different ways. Just to give you a heads up, when you're working maybe a homework problem, ask for the value. They're asking you for the output, the y coordinate of that min point. It occurs at a input of x equal to 2. So there's our relative minimum value. So we've got our 2 turning points. Now this graph has no other turning points. Goes up to infinity, goes down to -infinity on the left and right side of the graph, left tail and right tail. Now, those 2 points lead us directly into our intervals of increase and decrease. So let's go ahead and observe that. So where is our graph increasing? Let's put our increasing interval down here. So we actually have 2 increasing intervals with this graph. All right, I'm going to go ahead and write those intervals. And the first interval we see is an increasing interval, right? As we're looking at this graph, as it comes from -infinity on the x-axis, I'm going to shade it in right now. So if you look between -infinity and -2, what is your graph doing? It's going up. It's increasing in value. There's an increasing interval. So all x values, excuse me, less than -2. So -infinity to -2, all x values less than -2, the graph is increasing in value. So again, there's that increasing interval, right? Now, as you look at our graph, as it turns at the turning point at -2, right, we get into a decreasing interval, right? So we have a decreasing interval. Let's go ahead and write that down. So where is our decreasing interval? So for all x values greater than -2, all the way down to our next turning point at +2. I'm going to shade it here in blue. Right? Between -2 and 2, between the 2 turning points, the graph is decreasing in value. It's going down from left to right. There's our decreasing interval, right? And then we're back up again. So as we look at the graph from -2, or +2, I should say, all the way to infinity, and again, we can shade it in here on the x-axis, the graph is back up, rising. So we have a second increasing interval, all x values greater than 2 to infinity. Right? So again, we've observed that graph, we've analyzed it, right? We've gone through the turning points, which again lead us to our increase and decrease intervals. And while we're at it, let's go ahead and write in the domain and the range. Right? Didn't ask for it, but again, we can see the domain. All the x values. This graph's continuous. There's no breaks in it. Has all real numbers. All real numbers x make up the domain. Right? And then as we look at the range, and this is true with all odd degree polynomials. When I say odd degree, our leading term, our term with the greatest power, has an odd number. So with that, we have a third, fifth, seventh. Odd degree polynomials always have a range of all real numbers because the end tails always go opposite directions. So it'll always cover the entire y-axis. So all real numbers y. But that's our range, right? So we're going to look at that. So we've analyzed that graph. So we've gone through the turning points, the increase and decreasing intervals. So that graph, they gave it to us. If not, we could produce it. So let's do that. Let's do one more example. Let's take a look at another polynomial, but we'll change it up this time. We'll look at an even degree polynomial. Right? Look at one with some little different look to it than an odd degree. Right? Let's talk about this even degree polynomial. And this is a quartic degree 4 polynomial. Now it says, again, find the increasing and decreasing intervals, list the max and the mins, and let's also state, add to our directions, let's state the domain and the range like we've been doing. So first thing we need to do is get a good picture. So get your calculator out. Let's go to our TI. Let's go to the y equal button. And let's store in this quartic polynomial. So 1.1 x raised to a power. I'm going to put the little up arrow caret key. Put in my power 4. And then I've got my x squared term minus 5.3x. Hit the squared key. The shortcut key with power 2. Plus 4.07, which is your constant term, which should be your y-intercept for your graph. Your constant term and a standard form polynomial is your y-intercept. But as I graph this degree 4 polynomial, and you get zoom 6, look at it on a standard window, you get a good picture of this graph. You can see this graph right now, again, looking at it, right, we can see everything we're looking for in this, right? We can see our turning points. We can see up here we've got a max, we've got 2 min points. So altogether 3 turning points in this degree 4 quartic polynomial. And with that said, we got a couple of increasing intervals and a couple of decreasing intervals to list. But before we do the intervals, the first thing we need to do is we got to find these points. This is important. Now don't hit the trace button on your TI calculator. This is important. Above the trace menu, you have the calc menu. We've talked about second calc menu. We've done it with zeros intersection back in our first unit. If you go in the second trace, you'll see commands 3 and 4, your minimum and your maximum commands. So you need to call those commands to find the exact location. So I hit minimum, and it asks a question on your calculator. It says, find a left bound down at the bottom or the top of your TI. Should be down at the bottom on yours. But a left bound, you see my cursor right now. It's over at negative 1.4 on the x-axis. Take your cursor and move to the left in the midpoint. Somewhere to the left, which would be on the decreasing side. And you hit enter to define a bound. So you mark it. It marks that bound for you. So you see that bound marked at negative 1.8, which is clearly to the left in the midpoint. And it's asking a new question at the top, says right bound. So take your right arrow, and you need to slide to the right side, anywhere to the right. Somewhat close to it. We'll look at a point to the right of it. Now that's on the increasing side, right, of this turning point. And hit enter, and it'll lock in when you hit enter a third time on that turning point. So you can see we have a relative min point at negative 1.552 on the x-axis, right, at that ordered pair. So there's one of our turning points. So let's go ahead and write down that point. So back over here, let's start with that one. So our relative minimum point, and I'm going to write down the point. Again, there's different ways to write it. You can write the value, which would be the y-coordinate. But the relative min point, and we have a couple of them. So let's go ahead and get ready to write both of them. But the x-coordinate, let's go 3 decimals. So we had an x-coordinate of negative 1.552. Right? And our value was negative 2.314. That was our first turning point. At that point, the graph changed from decreasing to increasing, right? And then we got a relative max point getting ready to come up. So let's go ahead and get that point too. Let's go ahead and find our next turning point. Let's go back to our calculator and do the max point, which if you look at, it looks like the y-intercept, 4.07. Now let's find that. So back into second calc. This time command 4 is our maximum command. So again, ask the questions. Left bound. Well, right now we're on the left side. We're on the increasing side of this turning point. Max point where it changed from increase to decrease. Hit enter. Mark you bound. And then you slide over and answer the right bound question. You need to be on the right side of the point. Clearly on the right. Hit enter. Enter a third time. And it locks in on your point. And you can see it is the y-intercept point. You can see down here the max, it says mine is 4.07, you remember, is the constant term. Now you might have a different x-coordinate than me. Mine says 0.00000, it's trying to give me a decimal for 0. Well, we know we're at 0 because our y value is 4.07, and that's what our constant term is. We would get that if we plug 0 into x, so we get the constant term. Now you might have a number like negative 1.56, but at the end it'll say e to the negative something. All right, so you might have an e to the negative number, which is introduced in scientific notation. That means move your decimal that many times or less. So if you had 1.5 e to the 6, you'd move it 6 to the right. But if you had 1.5 e to the negative 6, you'd move it 6 to the left. And that makes you put in your zeros. You're trying to get a decimal or a 0 decimal. So just remember on your TI, if you ever see an e to the negative number attached to your value of the x-coordinate, they're giving you the value of 0 for x. So keep that in mind on TI. So our relative max is the y-intercept point. So let's go back and write that one in here. So again, remember, you see the constant term. So our relative max point is the ordered pair, 0, 4.07. So we don't need to do any rounding on that one. Now we have another relative min point. Let's go ahead and get that. So going back to our graph, going back into second calc, going back to command 3, let's surround that point, get a left and a right bound, and you see it's at 1.552 negative 2.314, which is the exact coordinates of other point except the sign of the x-coordinates changed sign, and that's because we're looking at the reflection point across the y-axis. This graph has symmetry to it. We're going to talk about symmetry later on in this unit. This graph, again, you can see the y-axis splits it right down the middle. So this is the reflection point, which is the other min point. So there's our other turning point on this graph. So let's go ahead and write that one down. So negative 1.552, right, or we got one at 1.552, negative 2.314. So there are our turning points, and from there, right, we can go through and do the increasing, decreasing intervals. So we're going to go ahead and write in those intervals. So let's go ahead and look for those next. So where's the graph increasing along the x-axis? Remember, you're observing your graph left to right, and they're going to tie in directly, right, to your turning points, your relative min and max. That's why you want to make sure you find those first before you do these intervals. All right, so let's go ahead and look. So back to our graph. We can shade it in if we want. All right, let's look at it. I'll pull up my pencil here. So if you look at your graph, and we can go ahead and mark these points. This is negative right here, negative 1.552, negative 2.314. All right, and here's the other min point. We got 1.552. Negative 2.314. And then we have our other turning point right here at the y-intercept of 0, 4.07. But as we observe our graph, right, let's take a look at the first interval. So we go from left to right along the domain. Right, as we come from negative infinity on the x-axis. Well, as we look between negative infinity and negative 1.552 on the x-axis, right, our graph is what? Decreasing. So there's a decreasing interval, right? So we're looking at a decreasing interval in front of us. So it's decreasing from negative infinity all the way over to negative 1.552. And then what happens? And then my graph's going up, right? Rising. So for example, if you look between what? You look between negative 1.552 and 0. Let's shade that in here in red. Right? What is our graph doing in here? It's rising from left to right. So there's a increasing interval, right? It's increasing in value. So we can go ahead and write in that interval. So it's increasing between what? Negative 1.552 and 0. So between the turning points. And then we're back. We're back down again, right? We're back decreasing, right? So we're looking here, right? We can trace our graph. So between 0 and positive 1.552, let's go ahead and shade it in here on the graph. Right, our graph is decreasing. So we've got a second decreasing interval from 0 to 1.552, right? There's a decreasing interval. And then we're back up again, right? As we look from 1.552 all the way to infinity, the graph is increasing in value. So we have a second increasing interval. So 1.552 to infinity. So again, you see your intervals. So again, we can write down our answer now. So again, once we have our graph in front of us, once we have those turning points in front of us, right, it makes it easy to see that. So let's go ahead back to our answers. So increasing intervals, we had 2 of them. So we'll go ahead and write those in here in interval notation. So we had a increasing interval from negative 1.552 to 0 on the x-axis between the min and max point, right? We saw that increasing value. And we had a second increasing interval for all x values greater than positive 1.552 to infinity. And our 2 decreasing intervals, we began the graph looking at a decreasing interval from negative infinity all the way over to negative 1.552. And then where do we have our second decreasing interval? And we can go ahead and put that in interval notation. We had our second decreasing interval between 0 and 1.552. And let's go ahead and write in our domain. So let's look at domain of this. And again, domain are all the x values. And this graph was continuous, had all real numbers. There was no breaks, no undefined values. All real numbers x, negative infinity to infinity. Now the range, this is different from odd degree polynomials, right? We did have a restriction on our range values. Let's go back to our graph. So we look back at our graph, right? Let's go ahead and mark it up. Our graph, which is down here right now at our min value, let's put these 2 points back up here. So again, negative 1.552, negative 2.314. So if I were asking you, where does this graph take place in the y-axis? It begins at negative 2.314 on the y-axis. And it goes up forever. We could shade it in here in red. So here's my range, right, of my graph, all the way to infinity. This graph goes up forever. There's our range values. So our range would be all y values greater than or equal to negative 2.314. All right, so that's the range of the graph. So again, domain is x, which again, you can see the domain is all real numbers, covers entire x-axis. The range has some restrictions. So let's go ahead and write in our final answer. So write in our range. So again, negative 2.314, the minimum y value. As far down the y-axis our graph went. And it goes up forever. So we've analyzed that graph. So again, that's looking at different function graphs. Determine your turning points. Find those extrema. And that leads us to our behavior, right, where it's increasing and decreasing. And it also talks about our domain and range. So I hope that helps you with this section.